25 minutes, is that correct?
You are allowed as much time as you want.
No, you can't say that because this is an organization and the next person has to, wait.
Well, like, look for the time.
Well, what is my time? That's what I'm saying, because we're starting late. Is it 25 minutes or is it less than 25
It's
minutes?
25 minutes.
Okay.
We're not cutting the time anyway.
Okay, got it.
Hey, you alright? Good to see you. Alright. See you around, man. All right. Welcome to Adopting Bitcoin. Welcome to the developer track, the Galoy stage here. My name is Moritz from Spectre Wallet, but today I'll be moderating the stage here. I'm very excited to see you all. So we had quite some fun last week in LA. And let's hope the price doesn't go much more down, but it was quite some fun. We had some fun seeing all this funky crypto stuff burning down. So the first talk here today will be by Adam Gibson from Vexwim. Adam, please come up. A round of applause. Adam is working Join Market, and we'll talk about identity is a problem. And you have been quite some time, like the third time in El Salvador now.
Yep.
So you are almost a local. Okay. Yes. Perfect. The stage is yours. Here we go.
Okay, thank you very much, Moritz, and thank you to the organizers for this conference in this beautiful place. So I'm going to crack on straight away. So this talk is, it's a slightly cryptic title, Identity is the Problem. I'm going to be talking about attacks on privacy-preserving peer-to-peer networks, kinda. Also, my talk is about 1.5 hours long, but since I've got 25 minutes, I am now going to rapidly progress through the entire waffling first half, which I'm not going to. But you can read it. Nice thing about this conference, you can actually download the presentations on the website for the conference. So you can read this later if you find it interesting. Unlikely, but possible. Let's get on to attacks. So I'm going to start by, let's see if I got this right. Yeah. I'm going to start by talking about attacks, and I'm going to be focusing in this talk specifically on, by the way, guys, my timer is not on. It's okay, but I'm going to be focusing on 3 systems in particular, and obviously they're relevant to us as Bitcoiners. Tor is very relevant to us as Bitcoiners, at least for now. Lightning, well, it's one of the main reasons we're all here. And Join Market is something that I work on, which some people will know is a CoinJoin implementation. And calling them peer-to-peer networks is a bit sleight of hand. Some of them are more peer-to-peer than others. Is something wrong? No, okay. So, and I've noticed I've written over Tor exclam on the other two, because just think about how much of what we do as developers in this space or people using tools in this space depends on Tor. So what kind of attacks am I talking about? Well, because these systems are intended to be in some sense or other privacy preserving, it means that there is a problem where we can't really identify actors in them. So if we start thinking about attacks on these systems, we think about especially denial of service attacks, but also we can think about like probing attacks, things where people are querying and trying to actually break that kind of privacy promise we get in these systems. I guess the distinction between different kinds of denial of service is kind of obvious. You can denial of service a particular node. Somebody's offering a service, you can try and shut them down. Or you can just try and DDoS the entire network as well. So talking about denial of service prevention, here's an interesting quote from the CEO of Cloudflare a few years ago, Matthew Prince, saying, "Literally, I woke up in a bad mood and decided someone shouldn't be allowed on the internet, and he switched them off." Doesn't really matter who they were. The point is that centralized denial of service is very exposed to censorship risks. And unfortunately, that is the reality of the world we live in, certainly outside of these privacy networks on the main internet. We have very centralized denial of service. And even if you weren't worried about censorship, you should be worried about hacking. What happens if Cloudflare gets hacked? I think it's a very interesting question to think about. Might keep you up at night, but yeah. So centralized denial of service prevention is not a solution, especially because we're trying to keep privacy. We're trying to keep a situation where there aren't kind of registered identities, a database of people, or even keys, yeah? So thinking about Tor, as I said, Tor is really, time's working great. Tor is like a kind of bedrock of what we're doing. And it's I think I wrote in my description of this talk that I'm discussing here an urgent problem. Maybe that's over the top, but a lot of us feel like it feels kind of very worrying at the moment. We're all relying on Tor in a lot of ways for privacy in Bitcoin, in Lightning, and in some related systems. Join Market is another one. And this system is actually under attack. We're relying heavily on a system that is under continuous attack. Maybe it's not very heavy attack, but if I just like jump forward a bit to this picture, you can see here on their metrics page, Tor is showing, actually there's a clever way you can, yeah, doesn't this work? Yeah, oh. You can see there that around June or July, there was a sudden spike in the kind of latency, the delay on the Tor. Specifically, this is accessing public websites, but it's also true of Onion services. And the latency is continuing to be bad, and there are problems with the reliability of the Tor network. So it's some kind of denial of service attack. It's actually difficult for me anyway to get any information about exactly what's going on. But I have, if I just go back a second, there's an interesting paper from 2019 called Point Break that goes into some of the ways that denial of service can be executed on Tor. And they even have a nice table here where there's botnets you can buy and pay like, I don't know, a few dollars an hour, whatever it is, some really low cost, and just attack your darknet market competitor on Tor and just bring their service down. So this system is exposed to attack, whether it's actually being attacked day to day or not, and it kind of is being attacked day to day, so it's the worst possible scenario. I did notice that there's some code being written to implement a proof of work solution or a mitigation to this continuous denial of service attack on Onion services at the moment in certain Tor repos. I don't know in detail, maybe some of you have better ideas. But anyway, what do we think about proof of work solutions to this kind of problem? I think at best they're a mitigation, they're a short-term solution. The problem with proof of work as a defense against these kinds of attacks is that it somewhat favors specialization, or heavily favors specialization in hardware. As we know in Bitcoin, that's kind of like the story of Bitcoin to some extent. So it's maybe not ideal from a consumer perspective, from a user perspective, to use proof of work to solve these problems, but it is an option. Now I'm going to talk a little bit about attacks where people try to probe these networks to de-anonymize, to reduce the privacy properties. This is from Join Market. Very soon after Join Market started, we experienced, we realized, because somebody actually started to do it, that it was trivial to attack Join Market in a specific sense of there's a negotiation of UTXOs to start a coin join, but if you can get the counterparty's UTXOs first, then you're gaining information without any cost. So you can just simply keep querying over and over to see the UTXOs that different participants have, and to some extent or other, that can lead to either complete or partial de-anonymization of coin joins. So I'm not going to go through all this, there isn't time, but I think I want to get a concept across in your mind that in that kind of scenario, the attacker is getting information by continuously querying, and they don't just query once, right? They have to keep doing it. If they keep querying fast enough, then they're going to see the difference between a UTXO set at one point in time and another point in time, and they're going to be able to make deductions about what's going on in individual coin joins. So there's a sense in which an attacker is racing with the non-attacker participants in the network. If they query very slowly, they might not get very good information. If they query very fast, they might be able to de-anonymize everything. Very crude picture, but have that idea of a race in your head. And notice I'm not explaining a solution yet. Notice in Lightning we have a very similar dynamic. This is from a very recent paper last year analyzing privacy properties in Lightning, and they're looking again at a probing attack where they're probing balances in channels by making payment requests or payment attempts, and depending on whether it succeeds or not, they can deduce something about channel balances. But the same dynamic is at work here where in this graph, in fact, on the far left, you can see that you have a very short snapshot interval. So they're querying every second. In fact, I think they're doing lots of payment requests every second. I'm not sure exactly how it works. But in that case, the blue curve shows they're getting like a 75% success rate in identifying individual payments, like actually tracing payments through the network, which is exactly what the onion routing of Lightning is supposed to prevent. Obviously, there's a lot of background here, like how did they set up the attack? Well, they're talking about creating sending and receiving nodes, so they do need inbound liquidity. So it's not trivial to execute these attacks. But the crucial point, I think, here is that if you have very slow snapshot interval, like if you only snapshot every 100 seconds, well, the accuracy of your de-anonymization starts to get very weak. Why? Because payments overlap. It's the same principle. The transition, if you want to actually see everything that's going on, you have to snapshot between each state transition. If there are a million state transitions between your snapshots, you're not really de-anonymizing at all. So the point there is that you need speed. You need the rate of your querying to be high in order for these de-anonymization attacks through probing to work. Again, I am not explaining a solution yet, but that's the kind of attack. Now, does this attack happen in Lightning today? I think probably not, but it's not at all impossible that some people have done it a little bit here and there, not just researchers. And so it's really is a worry. This is more back on the denial of service angle. So remember, we talked about probing to de-anonymize, but we also talked about denial of service, just like stopping the thing working at all. It isn't really so obvious that jamming is much of a problem in coin-join style protocols. I mean, decentralized coin-join protocols. But certainly in the case of Lightning, there's a really obvious and serious problem of what's called channel jamming. You can split it into two types. I don't want to give you like electron channel jamming. I'm sure other people will do that, and other people have done that, and there are endless discussions and resources about this. But like crudely think of channel jamming as, well, it's easy for me to start a payment through your channel and then leave it hanging. So I don't fulfill the HTLC. I have open it, but I don't fulfill it. So you've got to wait. Your money is locked up while you're waiting for me to decide whether the payment is actually successful or just to cancel it. So the thing, again, it doesn't really cost anything to do that. I mean, you have to have a channel, so there's a sense in which you have to have money locked up, but you can really amplify the effect of that money you've locked up to block other people's channels. And a bit like that Tor example, you could have a competitor routing node, and you can just kind of block them up and have your routing node, in theory, maybe, make profit from that. So it's a very dangerous, or let's say a very worrisome attack, which there are many proposed solutions, and I'm going to be describing one kind of proposed solution next, because I'm now going to be talking about solutions. Now, these are certainly not full solutions, but it's, let's say, a direction towards solutions to these kinds of problems. So first of all, like an idealized framework, what would we really like the solution to look like? We would like not to be using identities, because it's very difficult in a network to talk about identities. When there's two participants, right? In a Lightning channel, you have, Alice and Bob at the two ends. Well, if something goes wrong, Alice knows that it has to be Bob that did the wrong thing, because there's only two people. When you have a network of lots and lots of participants, if you try and apportion blame, the problem is that what look like two different entities could be the same entity. That's called the Sybil attack, right? And so it could be that it's very difficult to apportion blame. So trying to make people pay after they've behaved badly is very difficult in these networks. So we tend to want to try to make costs up front, but costs up front are also difficult because who do you pay? Because there's no identities, right? It's very tricky. But ideally, we would like to make a cost to use the system where the cost is very, very cheap. So on the third line there, imperceptible cost for normal protocol usage, but very high cost for attackers. So I've drawn that kind of exponential graph is just the idea of, we sometimes call it a dog leg, something where at the start of the graph you can't even see anything, there's nothing happening, it's basically zero, but at the end of the graph it just goes crazy, right? It's incredibly high cost if the resource usage is very high, but it's very low cost if it's very low. That's what we would like to happen, but it's very difficult to achieve that for reasons that are obvious and also reasons that are unobvious. Now I'm going to sketch some parts of what I think is a sensible solution. The first part, and I've mentioned privacy pass, but really what I'm talking about here is the idea of Chaumian tokens. Now the privacy pass example specifically was, you want to browse the web over Tor, you have to solve captchas all the time, it's a nightmare, so you solve captchas and you get Chaumian tokens, and then you can use those Chaumian tokens anonymously to keep surfing the web, if that makes any sense to you. So, but the important point here is that there's some server, and it's, wow, that went crazy. There's some central server that is issuing these tokens, and it makes it easy for you as a low-volume user. If you just want to browse the web normally, you're not making a million queries, so you can get some of these tokens, and you can keep your anonymity without... So that's a Chaumian token concept. It's great. I think it's a really solid, promising solution because it keeps the user's privacy, but you can still impose a cost. The problem with it is, how do you pay for those tokens, right? If you want to... So how do you keep anonymity at that stage, at that step of creating, of paying for the tokens? Okay. So now I'm going to introduce the concept that was the solution to the problem I described in Join Market in 2016. And to remind you, the problem was that you could query to get makers, Join Market makers UTXOs for free. How do we make it not free? We forced takers, which is the people like starting the coin join, to provide a kind of a commitment to a UTXO up front. So they didn't spend the UTXO, but they proved they own one without revealing which one it was. I'm not going to go into the cryptography. It's a discrete log equivalence proof, but the flaw with that setup is that it required the taker to actually reveal the UTXO to the maker at the time of the coin join. So it didn't get revealed to the whole world, but it did at least get revealed to their counterparty. And that's limiting, because that means you kind of have to choose a UTXO inside the coin join so that you don't end up actually like revealing your whole wallet to everyone in the world. Okay, so that was okay. What I'm proposing now is something called Riddle, which is the same thing, but just making it more powerful. So I'm going to prove to you that I own a UTXO, one of 10,000 UTXOs. But I'm not going to reveal to you which one, and I'm going to create a tag. This is, by the way, those of you who know Monero will understand this. I create a kind of tag that proves I've only used that UTXO once, even though I've never revealed which UTXO it is. So that's the idea in Riddle, and I'm going to go a little bit into the technicals of that right now for a few minutes before kind of summing up how that fits in with the Chaumian token and the whole picture, yeah? Oh, sorry, this is the whole picture, yeah. So general overall picture would be use those Riddle-type constructs for high anonymity and low cost for an ordinary user to get access to the Chaumian tokens, then have the Chaumian tokens be the thing that the service provider, who could be a joint market maker or a Lightning Network routing node or anything, or maybe Tor, they receive those Chaumian tokens from you as an upfront payment for service, which is very cheap to you, but it stops the attacker because they haven't got millions of them. And then finally, also I think important is that on the service side, there should be some kind of throttling mechanism, because otherwise you don't get this non-linearity. The service side wants to say, okay, I'm fine with people paying a few tokens in normal usage, but if things start to look suspicious, like it might be an attack, I'm going to raise the cost dramatically, yeah? That's the kind of overall picture. Okay, this is a very nice, easy to understand slide. So why did I do this? Well, this is about 1.2 kilobytes in base 64, of course, but this is actually what I call a riddle, but it's a ring signature over about 6,500 taproot UTXOs on Signet between two blocks. So this is a real ring signature over about 6,500 keys. And notice I was able to fit it on one slide. So that's really cool, and it requires some clever mathematics, of course it does. Jens Groth, Jonathan Bootle, people who know those names will recognize this, and MRL, the Monero Research Lab guys, came out with Triptych, and it's all based on that kind of thing. And it's a ring signature, it's a linkable ring signature. It's really compact, it's logarithmic in the number of keys. It sounds really cool, and look, I did it and it works and it's great, but there is a big problem with it, which is that all of these kind of ring signature constructions, linkable or not, are linear in their verification time. Linear I mean in the number of keys. So you can make this really compact ring signature, but it's no good if it takes 10 seconds to verify that the ring signature is valid. You can't use that in a real system, yeah? So I've spent some time looking at this problem, and I've come to the conclusion I should say there are some really good schemes with very, very sublinear verification time of these kinds of objects, if you appeal to bilinear pairings, for those of you who know what that is. Problem is, SecP256K1 does not support bilinear pairings, so you'd have to have a whole bunch of machinery to somehow translate. I've talked to Polster and stuff, no, it's not really, at the moment anyway, that's not really a thing. But there is another direction we can go in. And to remind you, what am I talking about here? I'm trying to make it practically feasible to make ring signatures over 10,000 keys. Merkle proofs are log time verification, so they are sublinear verification. So there's a recent paper from literally this year called Curve Trees, and what they do in this paper is they show that you can kind of combine these things together. You can create a zero-knowledge proof of the opening of a hash function. Now, opening a hash function in zero-knowledge is generally known to be very expensive. You need like tens of thousands of gates in your arithmetic circuit. But if you use what's called an algebraic hash function, that's not true anymore. So this is what's called Pedersen hashing. And then the problem with Pedersen hashing is that what it does is it takes numbers input and then it takes elliptic curve points as output. And that's great, except if you want to then hash up a tree, you need the kind of object that's the input to be the same as the kind of object that's the output. And the solution to this is something called you can use a tower of elliptic curves or a two-cycle of elliptic curves. So I don't want to like bore you with details, but basically you can take the kind of scalar, like the coordinates of one curve and make them be equivalent to the points in the next curve, and then do that vice versa. I can explain it to anyone who cares about the details later because time's quite short. But this is some technical summary here. You can build a shallow Merkle tree, and why are we doing all this stuff? It's for this goal, that we can get a sublinear verification time on a proof of knowledge of one of the secret keys in a huge set of public keys, and have that in tens of milliseconds instead of 10 seconds, right? Which would not be realistic. That's the general idea. So if this is all gobbledygook to you, basically we can get, a proof of a big set of keys. It's a little bit speculative. There is code for this stuff, but I haven't figured out exactly how we'd use it in this context, but I'm pretty sure we can do that. And if so, we get the output that I'm looking for. So I don't know if anyone here knows, but Gleb Naumenko and Antoine Riard have looked into this problem, as well as many other people have looked into this problem. And they came up with the idea of stake certificates. And if you did read that, then you might be wondering, is he talking about stake certificates? And the answer is actually kind of yes. I basically am. A slight caveat in that the way they described it, they were talking about a zero-knowledge proof of a UTXO being a lightning channel, which is possible to do, but it's like technically difficult. But I think that's not a helpful, that part of it didn't make sense to me. To me, I don't really care if your UTXO is a lightning channel or not. The point is there's an economic commitment there. So I think the only thing that's important is that it needs to be taproot. Why does it need to be taproot? Because we need to have plain public keys. Hashes of public keys, specifically non-algebraic hashes of public keys, are going to be a pain to prove it. Well, it's not even that. It's the fact that we would have to all agree to actually reveal our public keys if they're not exposed on chain. So taproot makes these kinds of constructions work a lot better. And yeah, so just a zero-knowledge proof of knowledge of the key for a UTXO out of a set. Now, what set of UTXOs, you might be wondering? I think the logical thing is you'd have an epoch, between the current time and 10,000 blocks ago. There's different possibilities. And also, you'd probably filter it by size, because you don't want just any dust UTXO. You might have some minimum size. This is just a suggestion. There are many models. So this gives you a kind of tokenization of your UTXOs that is not perfectly, but very highly private, very highly anonymized. And I've linked here, this is the description, specifically that chapter 6 of that book that Gleb Naumenko and Antoine Riard wrote about this problem, where they describe their overall framework. You'll find that their overall framework is a more detailed version of what I'm saying right now. So the problem about this whole thing of like solving, people might attack the system, is it's actually very difficult to distinguish between honest behavior and attacker behavior, right? It almost philosophically doesn't make sense to make the distinction. Probing in a lightning channel can be a useful thing to do. It can allow you to decide if a route is viable, yeah? Payments can be streamed, so a lot of payments doesn't necessarily mean an attack. But of course there's a difference between lots of small payments that succeed and lots of payments of varying sizes, half of which don't succeed. That's more suspicious maybe. Channels can be faked, as I already said. So there's lots of things where you've got to be careful to decide what you mean by an attack. And it's almost better to try and pull away and say, I don't even want to think about the concept of attack. I just want to align the costs with the resource usage and then not decide if something is an attack or not. That's the ideal. Again, coming back to ideals. And that's kind of related to what I mean when I say identity is the problem, not the solution. You know, we built these kind of networks to remove the need for trust in third parties or trust in any parties. So we're trying to make systems where it's the cryptographic verification that counts. And so trying to reintroduce identities, which we tend to do when we talk about reputation and web of trust, is kind of going the wrong way, in my opinion. So here's we're coming to the end now. Here's a sketch of what I'm basically trying to suggest. Sorry, that's a lot of text. That is a lot of text. So the idea would be use these Riddle type constructs, these zero knowledge proofs of UTXOs, to buy Chaumian tokens from service providers. Who are service providers? Could be Lightning routing nodes, could be join market makers. I don't know, you could do this in Tor, I suppose, you know, Tor relays, not sure. But anyway, just in the Bitcoin world, you could think about Lightning. You buy the Chaumian tokens from the routing node. That allows you to, it makes it even easier for the user that they can buy tokens when it suits them. You could say it also makes it easier for attackers, but then it comes back to that question of, you know, like, are you going to throttle usage based on what traffic you see as a routing node? So this kind of sketches out what you would hope would happen. In baseline operation, the cost for an ordinary user is trivial. They've got UTXOs in their wallet. They can prove without revealing what UTXO it is that they own one, and that could hopefully be enough for everyday usage. Somebody who's just making 5 payments a day, 3 payments a day. I don't know, let's say. So ordinary user won't see any cost, maybe, we hope. You could add on a reputation layer in a very lightweight way where you say, okay, as long as everything's normal, I'll just accept the fact that this guy, he's sent payments through me before, he's behaving well, I'll give him some reputation tokens. But as soon as things start to get weird, like you're starting to see too much traffic, you can start to get more serious. Say, I need Chaumian tokens, but I also need more Chaumian tokens for you to route through me. In the limit, probably the best thing about this suggestion is in the limit of somebody really attacking the network with thousands and thousands of, you know, requests around an hour or something. It's actually almost going to be infeasible for them because they need to have so many UTXOs that they're creating, recreating, and so on. All of this is debatable. It's a very kind of vague picture, but I hope you get the gist of what I'm saying is that we can try to defend against these probing attacks using some very kind of indirect cost of UTXO ownership. So that's the basic summary. I've got some final thoughts here, but I think we'll just kind of leave it there. Yeah, so we can definitely use this kind of idea in join market to improve it. I hope something like this will be possible in Lightning because either this or something else is needed because these systems are very currently exposed to attacks from economic attacks and just general maliciousness. So hopefully some of the nastier attacks on Lightning could be addressed with this overall strategy. And there's my contact info, and thank you for listening. Yeah.
Great. Thank you, Adam.
I just say if anybody needs to verify my code signing key, it's there. Yeah.
Perfect. Thank you, Adam.
Thank
This
you.
was plenty of good ideas. Do we have maybe two questions from anybody? All right. Privacy-focused friends are hiding. I come up to Adam after the talk. You can download the talk.
Oh, there's a question there.
Oh, question here.
Yeah.
Open norms.
I was just seeing that note here that to use this efficiently, Riddles, you would need to use taproot, right? So that would mean that Lightning would need to transition to taproot channels, and also join market would need to move the liquidity over to the taproot address.
Correct, yes. Unfortunately, yes.
Perfect. Round of applause, please, for Adam here. And next up, we have a panel actually, about the state of Lightning, together with our friend Jeff and a few other fellas. Jeff, could you please come up here? And yes, can you bring up the chairs? All right. Okie dokie. So, who is like his first time here in El Salvador? Anyone? Okay, very good. And so we have some people coming the second time. So I'm really impressed how the state of El Salvador has changed, and the security situation has improved. When you walk along the streets, you can see a lot more people on the streets and going around.